The purpose of this video is to go over a few linear approximation examples in some detail. First, before I do that, let me just put up the picture of linear approximation so we all know, we all have an agreement on what we're talking about. So this is the picture of linear approximation. What we have here is we have some function y equals f of x. It doesn't matter what it is. The point is that what we're going to do is draw the tangent line at x equals a, right there, and that's the purple line that you see. What we're going to do is when we evaluate a function, normally we take some particular x value and plug it into the original function. Instead, when we're using linear approximation, we're not going to use the original function, f of x. Instead, we're going to use the tangent line, which we're going to give a special name to. It's going to be called L of x. I went over in class how you actually derive the formula for L of x, and it's in the book. I'm not going to go over that. I think many of you can figure out what the slope of a tangent line is and then use point slope form to get it, which is precisely how we got this, this formula. The important point is that we give it the name, we give the tangent line the name linearization, specifically of f at the center x equals a, and the equation of that line is this. So now, for example, if I wanted to evaluate find the approximate value of, let's say, f of 2, instead of calculating f of 2, I would calculate L of 2. So I would get a value that's not exactly f of 2, but instead I'd get one that's pretty close to it because it would be along the tangent line. In other words, instead of calculating this value, I'll just point to it there, instead of calculating that value, I calculate this value, and we accept that this is a pretty good approximation, that this value is going to be a pretty good approximation of this value. So that's what we're really talking about. Now, just to complete the terminology, if you notice, as I go from A to x along the x-axis, I rise from this point along the green curve up to here. Here's f of a and here's f of x, and the difference, the vertical difference between them, is called delta f. If instead I start at L of a, which should be exactly equal to f of a, and instead I calculate L of x, then I only rise up to this point, and you see we create this vertical distance, which is not quite as great in this example. It could be greater depending on what sort of curve we have. But what that does is it gives us an approximation of delta f. So these terms will come up in some of the problems that we're doing. So let's flip to the actual problems. So first, let's calculate the approximate, let's let f of x equal 1 over x plus 1, and let's calculate an estimate or an approximate value of f of 3.02, and also find the estimated or approximate value of delta f. In other words, the vertical distance that the function changes as we go from 3 to 3.02. So, recalling that the formula for the linearization is f of a plus f prime of a x minus a. We'll just put that up there so we can use it. What we want to do now is we want to choose an appropriate value of a. As you might guess, it's fairly easy to calculate a fraction when its denominator is an integer. So we're going to choose 3. In other words, we're going to, for part A of this problem, we're going to choose a equals 3. Now, I understand that many people listening to this get freaked out by the idea that you have to choose something. They say, I want a recipe, I want an exact recipe to solve a math problem. I don't really have any answer to that other than this topic doesn't work that way. You have to use some judgment, and you have to understand that if I'm trying to evaluate the approximate value of 3.02, a good choice of a, or a good choice of the center, is going to be an integer, which is going to be a equals 3. The next problem will have another way that you might choose that, that you might choose A, but it does take some judgment. So I'm going to choose A equals 3. And so with A equals 3, first of all, let's write out that f of x is equal to 1 over x plus 1. I'm going to need its derivative. I could calculate it through the quotient rule, but it's going to be a lot easier if instead I use the chain rule. So let's just rewrite it in this form, because then I can say f prime of x is equal to negative x plus 1 to the negative 2 times the derivative of the inside, which is 1. So that gives us negative 1 over x plus 2 squared. Make that a little cleaner. Okay, so if A equals 3, then that means that f of, let's see, sorry, we're going to find the linearization of x. I'm going to keep the color scheme consistent. So L of x is going to equal f of 3 plus f prime of 3 x minus 3. So that's going to equal, f of 3 is going to be 1 over 3 plus 1, and then plus f prime is going to be 1 over 3 plus 1 squared, or actually negative 1 over 3 plus 1 squared, x minus 3. So that will come out to L of x equals 1 over 4 minus 1 over 4 squared, which is 16, x minus 3. Okay, so the thing that we want to do here is we want to estimate, choose a different color, we want to estimate f of 3.02 by calculating L of 3.02. Okay, so L of 3.02 is going to equal 1/4 minus 1/16, 3.02 minus 3. So that's going to equal 1/4 minus, that's going to be 3.02 minus 3 is 0.02 over 16. Okay. Now, because we really want this to look nice, we don't want to just leave it in that form, we're just going to put this in the form of an integer. So this is going to equal 4 over 16 minus 0.02 over 16, which equals 3.98 over 16, which equals 398 over 1600, which equals 199 over 800. And that's the approximate value of f of 3.02. Okay, now that we have the approximate value of 3.02, let's find delta f, the approximate value of delta f, which is the difference between f of 3.02 and f of 3. Now, note that this number here, whatever that is, if I were to plug in 3.02 and 3 and simply subtract the resulting values, I would get the exact value of delta x, but I'm interested in the approximate value of delta x. So, just going back here, in other words, what I'm interested in really is this value. In other words, not how much the y value would change if I actually followed the original green curve, but rather how much it would change if instead I followed the purple line. So what that means really is that the approximate value, delta f, in other words, f of 3.02 minus f of 3 is approximately equal to L of 3.02 minus L of 3. In other words, this is the difference that I'd get if I followed the actual function. This is the difference that I get in y value if I follow the tangent line instead. So let's calculate that. So let's see that L of 3.02 minus L of 3 is going to equal, recall that L of x was equal to, purple, L of x was equal to 1/4 minus 1/16 x minus 3. In other words, that was our L of x. So this is going to equal 1/4 minus 1/16 3.02 minus 3 minus 1/4 minus 1/16 3 minus 3. So this here is equal to L of 3.02, and this, oops, and this is equal to L of 3. So this is equal to L of 3. Okay. Now, notice a couple of things here. First of all, these are going to cancel each other out. We're going to have 1/4 minus 1/4, and this is equal to 0. So the only thing that I'm actually left with here is this. So this is equal to negative 1 over 16, 3.02 minus 3. Okay. So observe that that's actually equal to this part of it. So in other words, this is approximately equal to delta f. Just that part of the formula is. This is, of course, going to equal negative 1/16 times 0.02, which equals negative 0.02 over 16, or negative 2 over 1600, which equals negative 1 over 800. So that's the approximate value of delta f. Okay. Let's go on to the next example. So use linear approximation to find the approximate value of the fifth root of 31.9. Okay. So the thing you have to recognize about this question is that what we're asking is, this is equivalent to asking, what is f of 31.9 where f of x equals the fifth root of x, or x to the 1/5. So what we're doing is supposing that we have some function here, which is like f of x equals x to the 1/5. What we're saying is, here's 31.9. What's the approximate value of that? Now what I could do is, it's going to be a lot easier to calculate that if I know to calculate the fifth root of 32 than it is to calculate the fifth root of 31.9. So what I'm really doing here is I'm going to draw in this tangent line, and I'm going to use the tangent line to approximate the function instead of the blue curve that you see. Now, how do I know that 32 is a good number to use? Well, the fact is that many of you I know are going to be computer science majors, and you should simply know the powers of 2. You should know them up to 10, really. So 2 to the fifth is 32, so we know that 32 is a number for which we have a really easy fifth root. I put that up there because these are numbers that you should really know. So let's see. All right. So now, oops, sorry, wrong page. There we go. There's our page. Okay, so since we know what f of x is, what we want to do is find its derivative. Recall that the expression for L of x is equal to f of a plus f prime of a x minus a. So here what we have is we have f of x equals x to the 1/5. So f prime of x equals 1/5 x to the negative 4/5. Just rearranging that a bit, that comes out to 1/5 fifth root of x to the 4th power. So we're going to choose a equals 32. So that gives us L of x equals f of 32 plus f prime of 32 x minus 32. So this is going to equal 2 plus 1/4 times the fifth root of 32 to the 4th power x minus 32, which is equal to 2 plus 1/4 times, fifth root of 32 is 2, and if we raise that to the 4th power, we get 16, x minus 32. So that gives us L of x equals 2 plus 1/80 x minus 32. We're being asked to find the approximate value of 31.9, so that gives us L of 31.9 equals 2 plus 1/80 31.9 minus 32, which is 2 minus 0.1/80. That equals 160/80 minus 0.1/80. That equals 159.9/80, which is 1599/800. And that's the answer. Sorry, I ran out of space there. Okay, let's do just one more. Example. This is one of the harder ones that appeared on Sapling, so I want to show you how to do that. So let's see. Let's go to this problem here. The resistance of a copper wire at temperature T equals 20 degrees Celsius is R equals 15 ohms. Some of you may have taken electromagnetism and physics and recognized these terms, but it doesn't really matter, because the point is that an ohm is a thing we can measure. It's the resistance. The temperature is something that we can measure, and what it's telling us is that the resistance is a function of the temperature. Now, I realize that when many of you were doing this problem, the question was, how did you even know that? Well, if you notice what they gave you here, they gave you in the problem dr over dt. Well, dr over dt is just another way of writing r prime of t. So what that tells us is that at some point there must have been a function r as a function of t. In other words, resistance is a function of temperature, and they're giving us the derivative of that function. Now, in this case, what I'm writing here, the blue function is r of t. Now, how do I know it looks like that? Like this U-shaped thing that's drawn the way I've drawn it? The answer is I don't. They never told us in the problem at all what that function was. What they did tell us is what the derivative of the function was at a particular point of tangency, and that's the thing you have to tease out of the word problem here. Read the problem carefully. The resistance R of a copper wire at temperature T equals 20 degrees C is R equals 15 ohms. So what that means is that if R is a function of T, then R must be on the vertical axis and T must be on the horizontal axis. And what they're telling us is that at a value of T equals 20, right there, R has a value of 15. So essentially, the information that they're giving us is R of 20 equals 15. Or put another way, that the point 20, 15 appears on the graph of R of t. I realize once again why this is bothering a lot of you. We're being asked to deal with a function R of t that there's no formula for. The point of linear approximation is it doesn't matter what the formula for it is, because we're going to use this purple line to stand in for that function, and they are telling us how to find that. What they're telling us is that this particular point, the point 2015, is on the graph, and they're telling us that at t equals 20, in other words, right there, at t equals 20, the derivative of that function is 0.06. In other words, it has a slope of 0.06. That's all that we need to find, that's all that we actually need in order to find the linearization. Here are our givens. We have given R of 20 equals 15 for the reasons I just explained, and R prime of 20 equals 0.06. That's the information they're giving us in the problem. So what that means is that the linearization, let's stick to purple for linearizations, L of x is going to equal R of A plus R prime of A t minus A. I'm sorry, this shouldn't be L of x. We're going to switch to the variable t because that's the independent variable. And of course what we can see is that A, this is our value A, the center is A equals 20. Why? Because that's the point where that's the only point where we actually know what the derivative is, so we're going to have to choose that. So that means that L of t equals R of 20 plus R prime of 20 t minus 20. So that equals 15 plus 0.06 t minus 20. And then we're being asked to calculate, what does the question ask for? It asks for the estimated resistance at the estimated or approximate resistance at t equals 22. So what we're being asked to find is L of 22, which is going to be approximately equal to R of 22. Notice we can't calculate R of 22 simply because the problem has given us no information at all about what this blue function is. It's only told us how to find the purple line. So this is going to be 15 plus 0.06, 22 minus 20. So that equals 15 plus 0.06 times 2, which is 15 plus 0.12, which equals 15.12 ohms. And that symbol for ohms is the Greek capital letter omega, but once again, if you haven't taken electro, you don't need to know that. Okay, so anyway, these are the three problems I wanted to demonstrate. Hopefully this helps a little bit with the topic of linear approximation.